the laser? Yes. Okay. Hello, everyone. This is me. I'm Ryan Thomgren. Thank you to the remaining organizer for having me. Oh, two organizers still left for having me to talk to you about crystal and SPTs and associated mathematical objects I've been investigating with Dominic Else. He's at UC Santa Barbara. And I don't have time to go into the whole mathematical framework, so I thought I would just send you on a little rocket ship journey through 1 dimension, 2 dimension, and 3 dimension, all talking about parity symmetry. This is kind of a fun symmetry to think about because it naturally has a hierarchy. This is the symmetry where you reverse the sign of all of the spatial coordinates. So you take any hyperplane, parity restricts to parity on the hyperplane. So we're going to talk about how the phases in different dimensions relate to each other. See some fun geometry. Okay, so 1D, 2D, 3D. We begin with this curious one-dimensional phase. This phase is a kind of non-trivial paramagnet, so its ground state is a sum over all spin configurations. So I've denoted the spins in this classical X basis, either right or left. There are these green sites. There's a reflection center here in the middle, which reverses the directions of all the arrows, and also exchanges the sites with each other across the reflection plane. It's the ordinary reflection symmetry you would guess. But the funny thing about this state is that in the sum over all configurations of the spins, there are signs in the wave function weight. And the sign that you compute is different on the left side of the rotation center than on the right side of the rotation center. On the right side of the rotation center, we're going to look for bonds which have a right-left. On the left side of the rotation center, we're going to look for bonds that have a left-right. So in orange, I've denoted the bonds that contribute a sign to the wave function weight. So here, well, it's only this bond, left-right. This is a reflection of this state here. And now we have 3 bonds that contribute minus signs, so left-right on the left side, right-left, right-left on the right side. So it's actually reflection invariant, which is kind of hard to see from the definition, but I'll be able to prove it for you soon. Okay, so the first cool thing about this state is that when you apply a magnetic field in the x direction, we can do so in a way that preserves the reflection symmetry, having it be one sign this way and the other sign the other way. So the perturbation to the Hamiltonian looks like this. So both x and sigma x are odd under reflection, so this is symmetric perturbation. And as long as this is a ground state of a gap system, we can think about what happens to it. And basically it freezes all of the spins except for the one at the reflection center. And now if we look at our wave function weight, which should be the same, we see that actually if you apply reflection, you get always a minus sign. So the ground state, you can write it this way. It's a product state where you have, it's just frozen to be left, to the left of the rotation center, right, to the right of the rotation center. But on the rotation center, it has eigenvalue -1. So you can kind of think of reflection when you restrict to the reflection center in the presence of this magnetic field, so the reflection center is kind of like a domain wall. You have an internal symmetry, actually. So reflection sends the reflection center to itself, flipping the sign of the spin, so we see we have an odd charge under the induced internal symmetry there. Hiro? Yeah, so this is a good question. I didn't just pull this state out of a magic hat. I have some mathematical framework that produces them. And it's actually impossible to create a non-trivial phase of this class with the reflection center on a bond. You needed to have it on the vertex. And I'll tell you why that is in a second. Maybe it's the next slide. So we have a charge bound to the reflection center. That's the interesting point. You can detect this charge by computing a trace. So this operator, e to the minus beta h, when you take beta to infinity, projects onto the ground states. And then we insert this r, so we're just computing the eigenvalue of the ground state, and we said that this is -1. And if you think about this in a space-time language, then what you do is you take your space, which for us is just an interval, and then you have a circular time direction, and you insert the symmetry operator at some point in time. And you compute the partition function on that background. Well, our symmetry operator acts on space. It flips it around, so when you glue it together, you get this Mobius strip. Here I've indicated the boundary condition for the spins. And you compute the partition function on this Mobius strip with the boundary condition, and it's equal to this trace, and you get -1. So this Mobius strip partition function exactly is detecting this odd charge at the reflection center. Okay, so there's a way I like to think about the mathematics of these phases. It's working on the lattice. I like to work in the continuum, really, with like gradients and wedge products and things. And we can actually do these sorts of things on the lattice, but what we need to choose is something analogous to a coordinate system. It's a branching structure. And what a branching structure is, it's just a local ordering of the vertices. So you may as well think of it as a total ordering or something, where here I've indicated the ordering with arrows now orienting the bonds. And these are not dynamical, these are just fixed. Although the physics doesn't depend on them. It's like a coordinate system. And I've chosen the branching structure where the vertex at the reflection center in the middle is the highest in the ordering, and this one is less. Okay, so I've indicated it's an ordering of the vertices that I've indicated with directions on the bonds. Okay, now I choose a convention so that I can write this right-left as zeros and ones. So I'll choose right to mean 1, left to mean 0. And now with my orientation, there is a way of defining the derivative of this function. So this derivative is defined here. So on a bond I to j, it's just the j value minus the I value. So I wrote it here, so you get, this detects where there's a domain wall. So here's a domain wall, here's a domain wall. And the wave function weight that I told you about that looked funny, because it looked left-right asymmetric before, I can actually write in this very compact form, which you should think of this cup product. I won't define it for you, but it's like wedge product of forms. So this action here, well, not action, this wave function weight, is a lot like the nonlinear sigma model NDN. So it's just a discrete version of that. And you can see up top, I computed it for you in this example state, and it's manifestly reflection symmetric, even though these two weren't. So, right, if you plug in this formula and you know what cup product is, then you can show that it's the same as what I told you before. But the thing that I like about this, one thing that I like about it is that it's easy to show that the state I told you is symmetric. The symmetry sends a right spin to a left spin, so it toggles phi by 1, mod 2. And it also changes the direction of the bond, so it also negates the sign of the derivative. But that doesn't matter, because this wave function weight is just a sign anyway. And you see that, like an SPT state, the wave function weight is invariant up to a boundary term. Okay, so things we like to ask about SPT states is, well, this state is entangled, so we would like to ask whether it can be connected to the trivial paramagnet, where you don't have any signs weighting the configurations, by some reflection symmetric unitary circuit. So a unitary circuit looks like some unitary operators that apply on some bounded region of sites neighboring each other, and you just finite depth, this is depth 2, and it has to be reflection symmetric, so you can kind of see that in the architecture of this circuit, but the operators themselves have to be symmetric too. Okay, so this is a question we like to ask, and we can prove it by thinking about what a reflection symmetric unitary circuit has to look like for this kind of state, and it turns out it has to just be a phase. And it has to be a phase that only depends on the difference between the two spins. It can't depend on the two spins individually, because that's changed by the reflection operator. Okay, so there's a natural guess, which is this phi d phi, if you look at this branching structure, so this is the one where all of the bond arrows go to the right, you can see that phi d phi is counting, so I drew the domain wall for you, it gets a -1 when the domain wall goes down, right? So this is the right-left bond. The left-right bond is when the domain wall goes up. There's no sign to this side of the reflection centers over here somewhere. So this is counting the -1 to the number of domain walls over 2. So you may as well just come up with, okay, well, we'll assign I to each domain wall, and it should work out. And this looks like it would give us a reflection symmetric unitary circuit, but the problem is, to this side of the reflection center, you have to use I, and then to the other side of the reflection center, you have to use -I. So there's no way to make this into a reflection symmetric unitary circuit, because I is not the same as -I. And so if you know about the time reversal symmetric SPTs in this dimension, or in any dimension really, its anti-unitarity does the same thing for you. This is a unitary symmetry, but it's orientation reversing. Okay, so another way to think about this, and to actually prove that there is no circuit, is to realize that you can obtain the state that I told you about by a path integral of something that looks like a Z2 gauge theory. It's not really a Z2 gauge theory because the symmetry that we're thinking about is reflection. So one of the things that Dominic and I figured out how to do is to think about gauging symmetries that act on space-time, but something like reflection symmetry is basically like thinking about time reversal. The Mobius band was an example where in the time direction you have inserted a symmetry operator. So you can kind of see from that inserting a symmetry operator around a loop in space-time means coupling to a background gauge field that has some non-trivial Aharonov-Bohm phase around that loop. And because it's an orientation reversing symmetry, that's tied to the orientation of space-time. So really this gauge field associated to reflection symmetry is determined by if there's an orientable cycle in the space-time, then there's no Aharonov-Bohm phase. If it's orientation reversing, then there's Aharonov-Bohm phase -1, in a sense. But anyway, we related the boundary state up here. You can show that it comes from the partition function with this weight alpha squared. And we can relate this to a partition function on a closed manifold by taking our Mobius strip that we had before and capping it off with a disk. So I drew the boundary conditions incorrectly on the right. They're supposed to point in so that they agree with the boundary conditions here. So this boundary is a circle where all of the spins point out. This boundary is a circle where all of the spins should point in. So you can glue them together and then compute the partition function from the gauge theory that I told you about. Turns out to be the same exact invariant for the time reversal symmetric phase in this dimension. And so this trace that I told you about is the same thing as an integral over this glued together manifold, which turns out to be this real projective plane RP2, non-orientable manifold. Okay, so if there was such a zeta d phi which could undo the entanglement, then I could just plug in alpha where d phi is. It's the same sort of object. And then I would know that half alpha squared is exact, is d of something. But because of the orientation reversal, it's a little bit subtle. I have to consider this equation in some twisted cohomology group. This should be h over 2. And it's just non-trivial exactly because we computed on a closed manifold and we found something non-zero. Okay, so this is actually a symmetry protected state. There's no way to assemble an R-symmetric local unitary circuit which takes you to the trivial paramagnet. Okay, but however, you really need to use unorientable manifolds. This topological response is actually 0 on every orientable closed surface. Okay, so a summary of this phase real fast. I used a coordinate system which was reflection symmetric to write this thing in some, with some equations. I showed symmetry protection is equivalent to non-triviality of some gauge theory associated to this state, and the gauge theory is non-trivial just by computing its partition function on some closed manifold, finding that it's -1. That -1 was exactly the charge, the odd charge at the reflection center. Okay, other questions about the 1D phase? We're going. Okay. So the story is pretty much like this in all dimensions, but it gets more complicated to draw. Here is a state for parity symmetry in 2 dimensions where you reverse both the x and the y coordinate. This is equivalent to a 180-degree rotation. I've drawn the rotation center in red here. Again, we're going to have spins that point left, right. I need to choose this branching structure. Branching structure clutters up the image quite a bit. I didn't draw the arrows on the diagonal bonds, but they're there. They're implied by the arrows on the squares. And there's a funny weight that our weight before was phi d phi, so now we do phi d phi d phi. So it's like n dn dn. It just goes up like this. And what we're looking for are triangles where in this triangle it goes 1, 2, 3 is the ordering of vertices. And we're looking for ones that go right, left, right. You get a -1. So I drew the domain walls in blue. In orange are the triangles which contribute a -1 to the wave function weight, and it's a sum over all the configurations of the green spins. The gray ones were just some boundary condition that you can think about. So this state, we can do the same trick. So we can turn on a symmetric B field. So both y and sigma x are C2 odd. So this is a symmetric perturbation. And you find that, okay, it freezes all of the spins to be right above the line y = 0 and freezes all the spins to be left below the line y = 0. And if you look at the triangles which can contribute, they are exactly the ones we had before. So the right, left, right triangle to the right of the reflection center, this one is always right, so we're just looking for left, rights to the right of the reflection center. This one, these 2 arrows should be pointing to the right, but to the left of the reflection center we have right, left, right, just means having right, left. So it's exactly the same state that I just showed you in 1 dimension on this line once we turn on the symmetric perturbation. So this is kind of cool. The parity symmetry in this dimension, it's just a rotation, it's unitary, orientation preserving, it's pretty much an ordinary symmetry. But when we get a domain wall, it acts on the domain wall as an inversion symmetry, as reflection. So this is because if you take a line and you rotate it over, it's the same as reflecting it. So this is a kind of symmetry transmutation as you go down a dimension. It becomes a different kind of symmetry on the domain defects. Okay, so if I want to do the thing I did before, where I detected the charge at the reflection center by looking at the partition function on a Mobius band and eventually on RP2, I do the same thing here. So I want to glue the non-zero y directions by a parity transformation, and I want to glue the y = 0 directions like I did with the Mobius strip. So the space, you have to kind of think about how to deform this picture into a cube, but it's doable. And the way to achieve this is to take a ball, a 3-ball, and just like in Professor Twift's talk, you identify antipodal points of this ball. So it's good he gave the talk, so you've already thought about this space. And we're identifying the northern hemisphere with the southern hemisphere by the parity transformation, right? A point here goes to here, a point here goes to here, a point in front goes to a point in back, a point back goes to a point in front. That's parity. Thank you. And along here, we have also an antipodal identification that turns this into a Mobius band. So we see inside this space, RP3, which is actually orientable. It's the same as the group SO3. There is a Mobius band sitting inside of it, and the partition function in the 3-dimensional theory can be restricted to the partition function just on this Mobius band. And so we see in the structure of the spaces themselves that we use as test manifolds the hierarchy of phases. Okay, so you can say this is a boundary variation of some alpha cubed. The phase is symmetry protected by the same arguments as before, just by checking the non-triviality of this class, which means you can integrate it on RP3 to see this. There's the cool thing in this phase where this term alpha cubed can actually be written in a more familiar, maybe Trin-Simons form, alpha d alpha. And this form is read as saying that the alpha flux has half-quantized alpha charge, which in this case, an alpha flux, and you need to read Dominic and my paper more to learn about this, an alpha flux is the same thing as a disclination, a crystal defect of an angle pi, which you can think of as like gluing together an upper half plane of this material. And then something funny happens at the intersection, or at the singularity. And because of that funny thing, if you apply two parity transformations, you get -1. So it fractionalizes the parity symmetry on the crystal defects. Okay, and then there's a 3D phase, you do phi, d phi, d phi, d phi. And this one is the wave function is counting the number of right, left tetrahedra. It's just like before. There's a way to get the previous state by turning on a symmetric magnetic field. You can detect the non-triviality by computing on RP4, which is now unorientable. This is an orientation reversing symmetry. And the gauge theory that you get, alpha to the fourth, can be identified with the topological response of this interesting time reversal symmetric SPT in 3 dimensions, on whose boundary there is this two-dimensional bosonic topological order that looks like toric code, except the way time reversal acts on it. Both electric and magnetic particles are Kramer's doublets. So we know that that's an anomalous theory. So it's related to that phase of time reversal symmetry. There's a related, there's a maybe unrelated time reversal symmetric phase, which could appear here too, but it doesn't appear because it's just about gravity, it's about backgrounds, it's not about symmetries. Anyway, this is a summary of all the parity phases. So parity symmetry alternates between being orientation preserving and orientation reversing. This is like RPN alternates between orientable and unorientable. In odd space dimensions, you can identify the phase with a time reversal symmetric phase. In even space dimensions, you can identify it with an internal Z2 symmetric phase, but it's always parity symmetry. And this dimensional reduction reflects the way RPN is embedded in RPN plus 1. Crystalline gauge fields are collections of lattice defects. In fermionic systems, this period 2 hierarchy is expanded to a period 4 hierarchy, because now you can have p squared as -1 to the f and p orientation reversing or not. So here are some dreams of mine. So we don't understand the bulk boundary correspondence, we just understand the bulk topological response of these phases. It'd be very interesting to figure this out, because we know that anomalous symmetries, when they become spontaneously broken, they have, how to say, their Goldstone modes behave in funny ways. You can see the anomaly left over in the Goldstone modes. So we would like to know about how that influences the physics of the phonons. Then another thing is, we know how to, at least in the ground state wave function, make something which binds interesting fractional charges or Majoranas or something to crystal defects. And this might be fun in like liquid crystals where the crystal defects can move around. And yeah, I guess that's everything on this slide. So thank you all for your attention.
Thank you. Questions?